Hello. Does it work? Yeah, I think so. All right. Good morning, everyone, and thank you for being here. Today, we're going to dive into Chrome exploitation. We'll go through the inner workers of Chrome architecture, focusing on the V8 JavaScript engine and its exploitation pathways. Turn it on. Yeah. So we'll start by exploring the Chrome architecture and the V8 pipeline to set a foundation for understanding how things work under the hood. Then we'll take a look at a vulnerability class named type confusion, which will serve as a stepping stone into discussing the three CVs for today. The first one predates the V8 Heap Sandbox. Then we move to modern sandbox here with the second CV. We wrap it up with the third one, which serves as a fresh example of present-day vulnerabilities. So technology is not with us today. Okay. All right. Haven't done anything. What's going on? Yeah. It's because I have too many slides, I guess. Nope.
We had the whole break to get this working.
Yeah, it was working. I think.
We did.
Yeah, but
I swear.
it's luck. It's better now than later. Yeah.
And we have some.
No, I don't see. Yeah, now it's back. Can we try with this?
Yep.
Yep. I see the projector.
Mm-hmm.
Yeah.
You good?
USB 3 required for this device. Okay. Do you see a signal? Does it work? Yeah.
This is the tough part of having demos on everybody's personal PC, but we're in it to win it.
Cool. Nice. Thanks, guys. Cool. Nice. So hopefully it's less boring now. As I was saying, so we wrap it up with the third and last one CV, which serve as a fresh example of present-day vulnerabilities inside Chrome. So let's get it started. My name is Matteo. I'm a content dev and researcher at OffSec. I'm Italian, based in Norway. And occasionally I play drums in a local indie band. So where do we start? Bit of context before we jump headfirst into details. Why all of this matters. So browsers are one of the most used software worldwide, right? So they are valuable targets for attackers. And they are always connected, so they allow for any bug can be exploited and then can be pivoted as remote code execution. They also demand speed, right? We always have like dozens of tabs open all the time on our browsers, so they need to be fast and memory efficient. That's why we have JIT compilers. And JIT compilers, as we see in a second, they are really complex software. And we know that complex software leads to bugs. So let's get a brief overview of Chrome architecture before we start. But today's focus is Chrome, and its engine, JIT engine, is called V8 on Windows. Why Windows? Because it's the most rolled out operating system in target in today's enterprises. So that's why Windows. This is That's going to have a brief overview on Chromium architecture. So as many browsers, Chrome's run on multiple processes. The main process communicates with multiple isolated rendering process through inter-process communication or IPC to keep the renderer isolated. But what is a renderer process and what it does actually? So each renderer process is responsible for rendering JavaScript, DOM, and CSS amongst other things. As you can imagine, the renderer process is the most vulnerable piece of the chain since it's ingesting all the untrusted JavaScript code. And to protect each renderer process, we also have the process sandbox, which is outside of the scope for today's talk. So we normally have a sandbox on top of each process, which is called process sandbox. But before analyzing the first bug today, let's discuss how V8, the JavaScript engine, works under the hood. Right? So from a bird's eye perspective, from a bird's eye view, that's V8 operation. So ideally it also applies also to other JavaScript engines for other browsers. But what do we have? We have a parser, an interpreter, and an optional compiler, right? So the parser is one responsible for processing the JavaScript source code. So it breaks into token and generate an AST, an abstract syntax tree. The AST is a structure which represents the code syntax relationship. And those tokens are barely like, if you have a statement like x equals 10, each token is a single individual representation. So the parser generates this abstract syntax tree, which basically represents a hierarchical structure of the different code tokens. Then we have the interpreter, which takes the AST, this tree, as an input, and generate bytecode. Bytecode is just an intermediate representation of the program, which is designed to be executed by the interpreter virtual machine. And the interpreter originally could just execute wherever JavaScript locally. So from the VM, it could just generate machine code and via the virtual machine and generate it. So back in the days, browser just had the interpreter mainly. But suddenly, we need, as we anticipated, we need speed. We need good memory footprint, right? So we need a better way to optimize the machine code. That's why we have compiler. So, and some of these compilers are just-in-time compilers, which means they are generating optimized machine code at in runtime, right? This is a more actual view of the V8 pipeline from 2022, so 2 years ago. What do we have? We have the parser, which again output an abstract syntax tree, and it gives it to ignition, which is the interpreter. Then we have, as I said, we can have just local context execution from the interpreter. However, one of the responsibility of the interpreter nowadays is to generate statistics and data about what's going on, which kind of function are executed, and this is done through the profiler. The profiler sends and marks as hot code whatever function is executed multiple times. So let's say we have a function that is executed like 10,000 multiple times, even more, and then at that point the function is marked as hot code or hot function, and this is signaled to the JIT compilers. Two years ago, we had two different JIT compilers, Turbofan and Sparkplug. So Sparkplug is the non-optimized compiler, and Turbofan is the optimized one. We'll see what's the difference in a second. So, but basically, whenever we have a hot code, so a function that might be executed a lot of time, then we kick in with the JIT compilers. They do their optimized code, and then the function gets executed. Sounds simple. So this is the actual today's pipeline. So there's a new actor called Maglev. So in December 2023, last year, Google introduced a new JIT compiler called Maglev that acts as a compromise between Sparkplug and Turbofan. So actually, we have a 4 tiers pipeline. So we have 4 actors that can execute code. Ignition in a more simple way, and then we have the 3 JIT compilers all three, they can generate different kind of optimized machine code, but they are fast and optimized in a different way. So, for instance, Turbofan, it's one that is generated the most optimized machine code, but it's also the one that takes a lot of time to produce that code. So in case we have some JavaScript code that requires to be optimized quicker, then we might use Sparkplug or Maglev according to our needs. So let's get now a brief review on JavaScript types, bytecode, and the entire JIT compilation pipeline. So how actually JavaScript gets executed in V8? As we say, ignition is not optimal. So the interpreter just executes JavaScript code through the virtual machine. So it's not optimized at all, the machine code that produces. But anyways, let's see how JavaScript code works behind the scene. So the interpreter, as we said, just takes bytecode as an input and executes it via the JavaScript virtual machine, right? And the virtual machine is responsible for executing the final bytecode, right? So, but what is actually bytecode in the end? So this is a simple example of bytecode. We have a function that adds 2 to the to whatever property, right? We are sending in. So we are calling the add2 function, and the function takes property x of an object and adds 2 to it. So the first line is responsible for loading an SMI. What is an SMI? It's a small integer into the accumulator. So in JavaScript virtual machine, we have virtual registers as a virtual machine. One of those registers is the accumulator, which is not an actual physical register as you would have in a CPU. The accumulator is just a virtual register, but this is very handy to do short operation. So in this case, we load 2 in the accumulator on the first line. Then we store the value in the accumulator into R0, so store A into R0, and then on third line we call getNameProperty, which basically we load the function argument A0, so the first one, into the accumulator. Next we add whatever we have in R0, in this case 2, and whatever we added to the accumulator value, in this case 13, because we are passing 13 as an argument. Then we will return on the last line 15 to from the accumulator to whatever calling function we had. It was just a simple bytecode example. So we also have just-in-time compilation as mentioned. So the interpreter generated code is not optimal, right? When functions are executed too often. And how do we solve this? With just-in-time compilation, right? But first off, we need to solve some issues with JavaScript, with the JavaScript language. So how do we store type information? As JavaScript is a dynamically typed language, the engine must store type information with every runtime value. In V8, this is accomplished through a combination of pointer tagging and the use of dedicated type information objects that are called maps. Here we have all the different kind of objects that we can have in the JIT engine. Basically, we have SMI, basically small integers, and everything else is a heap object. So the engine treats everything as a heap object, right? And among these objects, we also have something called map, which is really important for our focus today. In the end, the engine is marking as the least significant bit 0. Anything that is an SMI, and with 1, anything that is a heap object. So the least significant bit plays a crucial role in how the engine treats object or small integer. So we mentioned that JavaScript is a loose typed languages, so the compiler doesn't know the data types in advance. But it learns from the past round and guesses how the code will be used in the future. And it makes optimization based on those assumptions, like creating faster code, assuming the types will stay the same. As we mentioned, how actually does JavaScript keeps track on data types. More on that in a second. But in C++, for instance, we have this simple function that adds to integer, and we can produce fairly consistent assembly code, right? Because it's a language with strong types, right? JavaScript, however, on the other end, it doesn't. So we don't know which values will be passed to this function beforehand, right? So we need to keep tracks of data types. How we do that? With maps. There's a really key feature in V8, in the JavaScript engine, but they also referred as hidden class in the JavaScript specification, or shapes in SpiderMonkey, which is the JavaScript engine for Firefox, or butterfly structures in JavaScript core in Safari, or hidden types in Chakra, which is the old Edge. So really not confusing at all. But in this case, maps. So V8 and Chrome, they use maps, so we'll stick with this terminology for now. And in this example, we have an object with two properties, 1 and 2, so two small integers. So let's see how they do look like in memory. So whenever we need to debug something in V8, in the JavaScript engine, and we compile it, we don't need to compile the whole Chromium project because, by the way, it takes like 5 hours on a beefy, even more, on a beefy PC today, so it takes a lot of time compiling the whole Chrome. We just need to compile V8, and it comes with a handy tool called D8, which is the debugging engine. So we can debug V8 through D8, which can print a lot of different values that normally we wouldn't be able to. In this case, we are printing object1, and in the green box, we have the array, right, with all the elements of set, and then in red, we have the map, okay, at that address. Let's add a second object with similar types, with the same types values, but different values, actually, same type, different values. So guess what? We just print object2 in memory, and we have the same map, meaning that object with the same maps, they will share also the same map in memory. This is a way for V8 to be efficient, so we don't create a new map for object that share the same types, right? And they also share the same fixed array. So we mentioned turbofan in the beginning, which is the optimized JIT compiler in V8. Let's see how it does look behind the scene, right? So it's the optimized JIT compiler. We have 3 JIT compiler now. We have Sparkplug, we have Maglev, and then we have turbofan. And it basically takes a bytecode from the interpreter, and it creates an intermediate custom representation, also IR, which is a graph, basically, with nodes, which are code operation, contraflow edges, and data flow edges, which are the input and output of the bytecode. So how it does operate, actually. An IR graph is built by analyzing bytecode and type profiles, formulating speculation about types, and possibly guarding them with speculation guards. More on that later, on speculation guards. So once the JIT compiler is happy with the graph building, it starts with the important phase of optimization. So the JavaScript is improved, and the memory footprint is reduced. And then we have the last phase, which is lowering. So it basically pushes the optimized machine code to memory for optimal execution. Cool. So we mentioned speculation guards. What are speculation guards? So there's no guarantee. We have no guarantee that the maps will stay the same for a given object in time, right? So JavaScript is a dynamic language, so that changes. Ignition, the interpreter, generates feedback, which is used by turbofan to make speculation about the type, right, of a given property, for instance. And then turbofan uses something called speculation guards to make sure that we don't have bugs as much as we can. We don't have bugs that are hitting type, right, of a property. So in this case, we have 2 examples of I'm not sure if the pointer works, but the first one, it's the speculation guard to make sure that we are dealing with an SMI. We mentioned at the beginning that every SMI has a least significant bit as 0. We're making sure that if not, we bail out. So we tested that actual property is a small integer. If not, we bail out. What does it mean we bail out? We don't crash the process, obviously. Otherwise, it wouldn't be reliable. What we do here is we simply de-optimize the machine code. So we go back to the interpreter and tell the interpreter, OK, just generate not optimized code, because clearly we have something wrong going on. And we cannot risk of using a map that is not that is not representing the correct type. In the second example, we actually checking the pointed by RDI on a given map. And if that pointer is not matching the given map, then again, we bail out and de-optimize the code. That's in general. So let's move on to JIT. So everything is nice and fun. We have JIT compilation. And we mentioned that we can have something called hot function. In the beginning, we have something here, an example of a hot function. So it's a simple function that adds to property of an object and execute that function several times, 10,000 times here. And we assign I to both property A, B at runtime, right? So at this point, the interpreter should be smart enough and signal turbofan, hey, we have an hot function. So this stuff gets executed a lot of time. We have to do something. We have to produce optimized code. I'm not capable enough to optimize in code, right? So one of the optimization feature of the JIT compiler, turbofan, for instance, is something called redundancy elimination. In this case, again, we have a function named foo that returns the sum of two properties. These features, basically, it's a class of optimization in turbofan that aims to remove safety checks from the emitted machine code if it thinks it's unnecessary, basically. Here, we have the check on the object, right? The check heap object and check map 2 times, right? On the first block and on the second block. So turbofan just decides, okay, why don't we remove the second check? It's just repetition. It's unnecessary. However, are we really sure that we cannot have any possible side effect in between elimination? What can possibly go wrong here? Right, let's introduce a bug class called type confusion vulnerabilities, which is fairly new vulnerability class. So JIT engines are complex because compiling at runtime requires balancing speed, optimization, and secure coding. Bugs arises during JIT compilation due to missing checks. That's basically what are type confusion. So as we said, JIT engines are highly complex systems, so we have high chances of bugs. The JIT engine assures that data is of one type at compile time, okay? However, due to side effects, unforeseen side effects of JavaScript operation, sometimes at runtime, that data type changes without the related type checks. So we are missing the right speculation guards, for instance. And then we can have something that goes wrong here. So type confusion might lead to out-of-bound read and write, and ultimately code execution. So the important key takeaway here is that we have a logical bug that turns out to be a memory corruption bug, which can open also a discussion on Rust, on safe programming languages, and so on. But let's not digress. Let's discuss now the first one of the 3 bugs. The first bug here is a very typical type confusion and predates the Heap Sandbox. So we can get a sense of how V8 bug can get exploited without extra mitigation. So this is a bug that's been filed by Samuel Gross from Project Zero, which is, by the way, he's also the author of the modern V8 Heap Sandbox. This line, the yellow part is basically the root cause of the bug. So here, the k-no write operator states that the engines assumes that this operation will not have any observable side effects, right? So basically the objects map here change without becoming a prototype. So what's happening here is that we call the map get object create map. So what this function does basically generates a new map for a given object. However, the newly created object is converted to a prototype object, which also changes the object associated map. This is a kind of unforeseen side effect that the JIT compiler hasn't taken into account. So we have something also called maps confusion. It's just my definition, but it's also a specific type confusion when you're actually confusing maps, which happens a lot of time in JIT engines. In this case, we are analyzing the buggy code, the bug in V8 version. So we print the object, we invoke the vulnerable function, object create, and then we print again the object and see what happens. So the first time we print the object, we have a map of fast property types. The second time, the map changes magically. It's dictionary properties now. That's not good because we should have a deterministic map as much as we can. If the map changes, and the type is not checked, we are able to abuse this situation. So I'm not going to cover all the exploitation steps because that will require a lot of time for each bug. But from high level, whenever we obtain relative read and write primitives, from that we can obtain arbitrary read and write primitives. And then what about code execution? So we are able to write and read in the V8 heap arbitrarily. So how can we execute our shellcode? Especially because the V8 heap has NX, so we cannot execute code here. Page are read-write, but not executable. What do we do? Let's enter WebAssembly, and specifically WebAssembly shellcode. So WebAssembly is an in-browser client-side aid for lower language type like C, lower level support for C or C++. It's compiled by another entity called a liftoff in Chromium. And we also, to reference WebAssembly code in V8, we have something called jump table. Basically, they are jump table to WASP function, to WebAssembly function, and those pages are read-write executable. So, yay. So we can basically execute one shellcode and reference it from V8 heap. So this is the first demo, which is pre-recorded. Here, we can just test the whole exploit and get reverse shell from our Kali Linux. Cool, that's the first one. Moving on, second CVE. This is a modern era sandbox bug from last year. It affects maglev. We mentioned the new compiler, maglev. This bug has been discovered by Man UMO from GitHub Research. So as anything new with any software, it will bring bugs to it, right? But before analyzing the bug itself, let's first explore what is the purpose of the Heap Sandbox, which is one of the goals of our presentation. So we mentioned the process sandbox at the beginning, right? The process sandbox is the sandbox that is actually protecting the entire renderer process or other Chrome processes. This has nothing to do with that. So this is a sandbox that is supposed to protect the actual heap in the renderer. So, so up until now, we needed just two vulnerabilities to get system foothold via a browser exploit. So we need two, basically, vulnerabilities, one on the renderer and one to escape the process sandbox, right? And we could get on the host. Now, the situation is a little bit complex, more complex, so we need three vulnerabilities, or like two bugs and one bypass. So again, the renderer, then we need the heap sandbox bypass, and then the process sandbox. So the cost for attackers is definitely increased. How does it work? How the V8 heap is actually working? So has been rolled out around 2022, 3 years ago. It's software-based, and it runs in an isolated heap. So the V8 heap is contained basically in the sandbox, referred also as a cage or Uber cage, which is a predefined memory region that is defined at startup. And we have something called pointer table, which is the essence of these sandbox, basically. So objects inside the heap are referenced via offset and indexed into a pointer table that exists outside the V8 heap. So what's the deal with that? Basically, we don't have full pointers anymore in the heap. So what were possible in the past that we normally, in a typical bug like the first one we mentioned today, we had something called backing store pointer in an array buffer. This is an array buffer dump. In yellow, we have in the first output, we have something called the backing store pointer. So we have a full pointer that can be abused to obtain arbitrary read and write primitives. And with the heap sandbox, we don't have it anymore. We just have a 45C, which is an offset to the jump table. Not jump, how it's called? The pointer table, sorry, not jump table. However, we have an offset, not a full pointer anymore. So we cannot do much, right? So we just have an offset. So one of the goals of the heap sandbox is to remove all the pointers in the V8 heap. So attackers, even though they get read and write access into the sandbox, they cannot abuse it that much, right? So let's go back to the second CV and its analysis. We mentioned that maglev is a new compiler rolled out last year. It's a mid-tier compiler that balances efficiency between Sparkplug and Turbofan. It generates less optimized code, but it does it quicker than Turbofan. So in some cases, you wanna use maglev instead of Turbofan. This is just done behind the scene by V8. You don't have to configure anything, but this is a logic that is implemented in the engine. The bug itself is a failure check while creating a default receiver object. Again, the same map is used for a different type. Sounds familiar? Again, maps confusion, which leads to type confusion. Okay. What's the deal for us? So standard WebAssembly shellcode is not possible anymore due to heap sandbox. So we cannot reference it anymore. But we can still read and write some function pointers, right? Because we mentioned that the heap sandbox has been rolled out 2 years ago, but until recent times it wasn't fully completed. So they rolled it out, but it wasn't as perfect as it is today. It's not perfect today, but it's better. So back then, last year, not every pointer was actually an offset. That's the whole point, right? So JIT compiled function pointers are represented as full pointers in from the V8 heap perspective, so we can still abuse those pointers. How we do that? We can modify those function pointers to jump right into JIT Spring shellcode. So what the heck is JIT Spring shellcode? Let's see what it is. It's a fairly new technique. Like it has 1 or 2 years old, something like that. So basically, what do we have here? We have an empty function that is just returning 3 floats, 1.1, 2.2, and 3.3, right? Then we JIT compile that function. And as a last statement, we just print the function and see how does it look in a debugger. Let's see how does it look. So this is from WinDBG. So that's the JIT optimized code from that function, right? And what we see here in the red block is that basically that number is moved to R10, and we have the same for the other 2 numbers. So likely those are our floats, our 3 floats. And if we convert that value into double, that's 1.1. So that's our first float. But what's the deal? Why it's helpful, this? Well, what if we could treat this float data as a code and not data? So let's change those 3 values or float value in something completely that doesn't make sense, apparently, and 3 random floats and see how this looks like in memory. So we dump the same value, and instead of dumping the value, we disassemble it. And guess what? Those floats are converted to assembly. So we have 1 breakpoint and a few knobs. So the idea here, we can basically jump over those floats value that suddenly are interpreted. We can interpret her as instruction of our shellcode. And we jump over those unnecessary vem-mov keywords instruction that are not necessary. So basically, we jump between chunks of shellcode of our choosing. The only caveat here is that we can only encode 6 bytes at a time. So we have 6 bytes or shellcode and then the jump instruction. But we can generate that shellcode pretty easily with the pwn tools. I haven't found a better way to do that, sorry. But that's what we have. Pwn tools, we can write the shellcode as ASM, as always, as assembly, and then print it out as JavaScript floating points, right, values. And then we replace the this shellcode inside our exploit. So we have a tool that can generate that. We don't have to do that manually. So let's demonstrate the second exploit with the second demo. Yeah, here we're getting calc because, yeah, I was lazy enough to get a full reverse shell, but yeah, that's code execution on Windows. So the last CV that I'm going to present today is pretty recent. From the write-ups were for August. Yeah, cool. This is another type confusion found by Manu Mo, again from GitHub research. So this is another type confusion in maps via the prepare for data property. Basically, when an object structure changes, like property addition, a new map is created. And it occurs, the bugs happen while transitioning from one map to another without the expected checks. That's, again, similar to what we saw earlier, but in a different piece of code. So how do we perform the sandbox escape? So previously, we used JIT compiled pointers, but now in this latest version of the Heap Sandbox, the WebAssembly pointers are gone, so we cannot abuse those anymore. We have something else in Chrome called Blink, which is responsible for rendering web pages, like it processes HTML, CSS, layout, and DOM, but lives outside V8, so this is not part of the JIT engine. However, inside V8 heap, we can reference those objects by embedder fields in the heap. Obviously, those objects are referenced as offset, as we saw in the Heap Sandbox definition, so we don't have full pointers, but we just have offset. So what if we can cause a second level type confusion by swapping those offset? And yeah, so we basically have read-write primitive outside the V8 heap, so we are not actually bypassing the V8 Heap Sandbox per se, but we just live by the rules and, yeah, apply the read-write primitives by the offset, not the full pointer. So with that, basically, we are leaking the trusted cage base, which is the Heap Sandbox base address, so we can get full write primitives and locate the address of the JIT compile WebAssembly through the import target. So we have the import target function in the dispatch table, and then we hijack the code pointer of DOM rectx, basically the properties of this object, which is one of the objects from blink that Blink we are abusing, which lives outside V8. So basically, in the end, we are hijacking WASM, JIT code, when the exported function is called in the end. So under normal circumstances, calling a WebAssembly function alone will let it just execute it inside the WASM, so sort of sandbox with no interaction with the rest of the system. But this way, we are creating time confusion inside external V8 objects. So for the last demo, I decided to do it live on a box that it's home. Let's see if it works. It's a bit risky, but let's see. How do I share this? I think I need to stop presenting. Cool. How do I share? A second. Sorry, give me a second. Okay, maybe. Oop. Yes, okay, cool. All right. Can you see anything? Yes. So we have our Kali Linux listening on port 443. We have a web server in Python that's serving the exploits, and then we have the official Chrome build. A thing that I didn't mention that here to debug the whole exploit, we couldn't just have V8. We had to compile the entire thing inside Chrome because the object that we are abusing in the end, they are from Blink. So let's start Chrome with the no sandbox option, meaning that we are not going to test the process sandbox. So what we do here is that serve on the vulnerable server and the vulnerable, and then we get a shell on Kali. Yes, that's a full reverse shell. Yes. Thanks. So a few key takeaways from this. As we said, browsers are complex, high-value targets for attackers. Type confusion bugs will likely persist in V8 due to JIT engine nature. Because it's a complex piece of software, we're going to have bugs no matter what. However, V8 Heap Sandbox increase the attacker's costs, but as we saw, it's not bulletproof. So we're going to have bypasses likely until it's going to be rolled out with full hardware support, likely. Now, the end result is that 3 bugs are now required to get a full system shell. All the POCs for today, you can find it on this website. Thank you.